Welcome to the World Sewing Championships 2024. Today we are looking at multi-threaded programming. And I had originally planned on doing up a whole bunch of demo programs for this video, but I thought a better idea would be if I went and took you through some of my own projects that I've done, some of the code I've written, where I've used threading with a real world use case. And we're going to go over how I use threading, why I use threading, and at the end of it, we're going to decide if for each project I actually made the right decision in multi-threading that program. Because in addition to showing you guys some of the things that are available to you with threading, there are two other things that I want to touch on today. The first is how programming concepts at a very high level don't always change so much between languages. So today we're going to look at threading in both C and Python examples. And the second thing I want to get across is it's not always a good idea to introduce programming paradigms into your programs if it's not necessary. So that's why we're going to be deciding if I actually made the right call in threading it, because when you introduce threading into your programs, you do introduce a lot of overhead and complexity. So why would you even need to use threads? And if you do need to use threads, what kind of setup might you use? Well, first off, the most obvious one that comes to mind is if your main thread is busy with something, but you still need to run other tasks at the same time. So for instance, if you're running a GUI loop, like a graphical user interface, and the user clicks the button that does some sort of time, like a task that takes a long period of time, you don't want your GUI to freeze up on the user while they're still trying to interact with it while your main task is busy with that work. If you've got a network service and there's something like a heartbeat in the protocol, you want to still be able to run your tasks in the foreground while responding to that heartbeat automatically, so you might thread a network loop. You might also just thread an application loop. I mean, like if your main task is busy with something like handling user input, but you still need to be running some kind of application in the background, you might decide to do that. You can also have another paradigm where it's sort of like a main thread that spawns up a whole bunch of workers. So if you've got computationally intensive work or time intensive work, for example, like web requests or something like that, where you don't necessarily want to wait for everything to come back before you start your other work. And there are other things you could do for this, like async IO, but that's a bit outside the scope of this video. But essentially, if you've got a whole bunch of stuff that's not necessarily like sequential, like it doesn't have to happen one after the other, you might consider threading that out to get more efficiency out of your program. Now, there are a couple of topics I want to introduce so we can refer back to them later. So the first thing is, what actually is a thread? When you're programming, you can think of threading as sort of an abstraction given to you by your operating system, wherein you can program multiple things to happen at the same time. A lot of the times it's not actually happening right exactly at the same time, but the scheduler in your operating system is going to do a whole bunch of fancy things that's abstracted from you largely while you're programming for desktop platforms at least, to make them seem essentially to you like they're running at the same time. So if I had multiple things I wanted to run simultaneously, I could just use threads for that. Now this comes with a couple of caveats as well. So let's say I have multiple threads that are running at the same time that want to access the same bit of data. This is called a race condition, where two threads try to access the same data. One might try to modify, one might try to read, but essentially they're going to want to use that resource at the same time. And so there are things that you can introduce like synchronization primitives. So you might have heard of a mutex before, a semaphore, some high-level programming languages just call them locks. But there are a whole bunch of things you can do in order to ensure that that kind of thing doesn't happen, and we're going to be looking at those as well. Let's dive into our first example. So this program here I wrote at the height of the pandemic 4 years ago. Essentially my problem was this. My lecturers at uni were very slow at uploading recordings to our course website. And because I was on quite a tight schedule, I didn't really want to wait for them to upload the recordings if I missed a lecture. So what I wrote was this little script here that would join my lectures for me. For instance, you can see here I've got a timetable here. You can give it a Zoom link. And essentially, it'll just punch in all the keystrokes needed to join the meeting. It'll count down until the scheduled activity finishes, and then it'll punch in the keystrokes to leave the meeting while having OBS record in the background. So if we actually have a look at how this ended up working, now you might be wondering, Matt, why would you need threads for this? The answer is that you actually don't, except for one small problem that I had. So it joined the meeting great. It spun up OBS. Here I essentially just had, I'll make this a little bigger for you guys. Essentially here I just had, this little thing here that booted up OBS automatically and recorded it, closing OBS when the meeting was finished. The problem was that I came back from uni one day and I found out that OBS had stopped recording halfway through. It had actually crashed. So how do I want to deal with this? Now, my immediate thought a couple of years ago was, okay, I can just write this crash handling thread. And so what this crash handling thread does, if I can find it real quick, I think literally, yeah, here we go. All it did was essentially just create a thread, and then every 5 seconds, it would check if OBS was a running process on the machine. And if it wasn't, then it'd restart OBS, and essentially, I just have to stitch the recordings together. But it should only have 5 seconds of downtime. So why did I actually decide to thread that? Well, if we have a look at how this program actually worked. So essentially, what it did was it got the time until the next activity, and the main thread essentially just slept. Now here's the thing, guys. This is where we're going to decide if I used the right decision to thread here. So there's a couple of things to consider. If you are really switched on, you might notice, well, because I'm only sleeping one here because I want to display when the meeting ends, what I could actually do is run my crash handling thing in here. Like, why not, right? Why would I need a separate thread? And you'd be absolutely right. In this case, I did not have to use a separate thread for this. Essentially, why I'm showing you this is to show you, if my main thread had actually been doing something useful and not just sleeping, that would have been appropriate to use the extra thread. But in this case, I literally could have just run the crash handler in here while we sleep. But you might have noticed if that takes more than 1 second, then this might get out of sync and I might overshoot. So what I could have done instead of calculating time to sleep here, just like this, if I got the date time of the computer right now and just took a delta. So if this while loop here was instead of like while time to sleep, and then I sleep for exactly 1 second, if I took like a date time delta, like time of ending minus current time, then it would stay synced up. So I could have done that instead. I think threading was actually okay here because, if this takes I could still overshoot with that method. Because let's say, I start a check right before the meeting ends, and that actually extends beyond the finish of the meeting. I mean, really, like, the consequences of that aren't too bad, so you could very easily get away with not threading that. Like, who cares if you overshoot the meeting by a couple of seconds? But if this was an actual time-critical application, it would have been absolutely appropriate to thread there. But yeah, that's the first example. So how did I actually start up the crash handling thread? Well, it was actually very simple. So let's have a look here. Okay, it's literally been 4 years since I had a look at this program, so it took me a little bit to find it, but here is essentially where I start the thread. So threading in Python is really simple. You have to give it a target function, essentially, that you can run as your thread. And that might have something like a while one loop or whatever, so it runs permanently. And then you can give it any number of args. So threading in Python is actually really nice because you can pass as many args as you want. And they can be any data type you want. In C, it's a little different. You got to pass a void pointer, and there are a couple of things you can use to sort of make that a little nicer. But another thing I want to talk about is daemon equals true here. So in Python, essentially, what this means is that this thread is going to be linked to the main thread in terms of shutting down. That's essentially, for my purposes, what the most use of it was. So when the main thread shuts down, got my tongue twisted there, but if I set this daemon equals true, when the main thread shuts down, this other thread will as well. And then all you have to do is call start on the thread. So it's really simple to do threading in Python and pretty chill as well. Now, I'm questioning my decision a little bit to put the thread starting in a while loop. I think I kill it somewhere else, but yeah, do run equals false, and then I think it exits. So theoretically, I should only have one thread, even though it's in a while one loop, but it probably would have been a better idea if I had started this thread once and then had some sort of signal to start and stop the checking for OBS. So that's another thing you might want to consider, because threading actually incurs a decent amount of overhead. Like if you start and stop a thread, there's a bit of overhead there. So it would have been better if I had just threaded this once and then had some sort of signal between the threads that tells it to start and stop. But that's essentially this example. So this program right here is going to be another example of that first architecture we were talking about, where essentially we've got a main thread that's doing something and we want to run some kind of task in the background. So this program right here, this is going to be a C example. I actually showed this program off a little bit in my server video. I mentioned I have a distributed system I've been working on. This is one of the microservices that runs on that distributed system. And essentially the purpose of this program is it uses these little USB RFID card readers. So essentially, if I tap a card on this thing, I want it to execute some kind of event over the network, like talk to another service. So there's a couple of things that I use threading for with this one. Now, this essentially, if you think about what this program actually has to do, the first thing is it has to read from standard in, right? Like it has to read essentially the way these USB card readers work is that when you tap a card on this thing, it essentially just sends it like pretends to be a keyboard and it sends the ID of that card over standard in. So this program needs to have a thread that sort of just reads from standard in and waits for that to occur. So essentially you can see right here, I've got this is my, I call this the application loop. So essentially all this does here is read in a line from standard in, and then it'll execute the network event if it finds one associated with that event. Now, a couple of things here. So this is a networked service I mentioned before. So in addition to doing that, it has to do other things as well. So my protocol, or essentially my microservice architecture, has API endpoints that people can hit. So essentially, in the main loop, I also have to be able to respond to those events. So for example, here, I'm switching on the endpoint and I'm going to do something with that. So essentially, I've read some kind of network event, and for whoever comments about this stuff being unsafe, I have like checker, like make it like before we get to this point, I've made sure that it's in the correct format. So don't worry about this fancy stuff here. It's fine. But essentially the deal is like at the same time as I'm reading those RFID card events, I also have to be able to respond to API requests. And then at the same time as I'm doing that, in order to make things easier for myself, my protocol has a heartbeat, as I mentioned earlier. And so I need to have a network loop to handle network messages. So if I go over to my network loop program over here, so this is from my library, and this is a function that spins up that basically handles network events, right? So for example, it'll handle reconnections. Like if the connection drops, it'll handle reconnections. It'll handle like the protocol level events. So for example, sonar is my heartbeat type deal. So every time it gets a sonar, it has to automatically respond to one. If it gets a direct message, then it has to send that through the pipe that I'm using to talk to this main thread over here. So essentially what I'm doing here is I'm using threads as almost like an abstraction to make the development process easier for myself. Because you would be absolutely correct in saying you could take this thread here, this network loop thread, and just slap it into this while true loop here, like the main API loop, and sort of do an epoll on that, and sort of or you could even combine it with this. If you used epoll, you could even combine it with this application loop here and add standard in to your epoll. So you actually could do this all in a single thread, but in this case, threading actually makes the program easier to understand, provided you understand threading. So that's another thing I want to mention as well. Like this actually, having this network loop right here makes it so easy for me to spin up additional programs if I need to. So threading can also be a useful abstraction to sort of tuck away, well, not necessarily tuck away, but to separate parts of your program to make it easier to comprehend. Because if I just had all this stuff in a giant epoll with a giant switch statement in here, it'd get quite messy. Also, as I mentioned earlier, so C threading, essentially you've got P threads, they're like POSIX threads, and it's the same kind of deal as Python, like you give it a target function, but you have to pass in a void pointer. So you can have a struct. I have this struct here that I just, and you'll see in here, I just go ahead and cast that back to the appropriate one in here. And it's like, you just need to cast the pointer, like all the data in it, as soon as you cast it back to this type is going to be exactly the same as this struct right here. So it's actually not so bad. So we've gone over two examples of that first architecture where we've got a main thread doing work and we want to do something else in the background. So at this point, I want to show you guys some synchronization primitives. So the first one we're going to look into is a full mutex. There are a couple different ones. This is the first one because it's, in my opinion, probably the most easiest to wrap your head around. So it's a binary lock. There is two states. There's locked and there's unlocked. So essentially, as you can see here, I've got a pthread mutex lock being called on this right here. So the type of this is pthread underscore mutex underscore t, and you've got to initialize it and stuff. I'm not going to go into that in this video because this is a concept overview essentially. But what we do here is we lock the mutex because in my protocol, I have message IDs, right? And so every message ID needs to be acknowledged and things like this. So what happens is this network loop right here locks this this lock here, which is associated with this data structure. It pulls a handle off the queue. A handle is just a data structure I'm using to represent messages and things. And then it will go ahead and make that available again, and then write that handle through to this thread over here. So this thread should have some kind of receive. I believe it's done on poll. Yep, so on poll right here. And it's got an inter-thread delivery pipe, essentially. And it'll go through and handle this handle right here, see? So essentially what I'm doing is I'm locking the data structure, grabbing an item off the queue, making that available so that if any other thread wants to pick up a message ID, it knows this one's available, and then it writes it through to the main thread. So that's essentially what I'm doing here. And the race condition that you might run into here is if the application loop, because when the application loop over here is wanting to write this event, it needs to grab a free message ID to send off. So the problem you might have here and why the lock is needed is essentially if I have made this, like if I'm grabbing this off the queue, another thread might have made that available or stolen that or changed the data in some way before either of these threads are able to grab it off that data structure. So that's why you want to use a lock in this situation, because the message IDs, it might mistake it as being free, it might mistake it as being taken when it's actually not, and you could run into issues there. So we're going to swap paradigms for a minute and talk about the main thread, worker thread sort of architecture I mentioned at the start of the video. So this was actually a program I wrote at a previous job of mine about 2 years ago, and I didn't sign an NDA or anything, so it's probably fine for me to show you. But I'm not going to show you the whole thing, obviously, because I do want to respect that it's technically, I wrote it for them, right? It's their program. But essentially, the deal is we were working with a lot of GIS data, which is geographical information system. So a lot of mapping data. And our government, our local government, provided a ArcGIS based web tool that had all sorts of proprietary information that we wanted to be able to use. That, you know, like the government, they made it freely available, but you had to go onto this sort of like almost Google Maps ripoff and load in all these layers and things, and you couldn't export them. So essentially what I did was I went in and reverse engineered the web requests that the backend sent to the front end whenever I changed something. So let's say I wanted to add a new layer. What was the data that the backend sent to the front end? And can I reverse engineer that and put it in my own program? And the answer was absolutely yes. So I wrote this little program here based on my findings to sort of wrap their API in Python and grab all the information we needed from there and put it into some kind of like spreadsheet, right? So essentially that was the deal. And web requests actually take a decent amount of time to complete, especially considering we had thousands and thousands and thousands of data points we wanted to extract from this site. So what I went ahead and did, I wrote the single threaded version of this program, very quickly found out it was way too slow. So it was actually very trivial for me to thread that. And essentially, because I'd already written a single threaded downloader, right? So the sort of architecture I had here was, you can see I have, I've got a max number of workers that I let it have. And essentially what I do is I go through the entire input data set. I create a, you know, like a thread table essentially where I store all these threads. Let me just make this bigger for you guys. Where I store all these things. And essentially what I did was I split up the data set. I've got another function in here that generates that. But essentially what happens is I load in the entire data set and then I split that up depending on how many workers I want. And then essentially each worker thinks it's its own thread, or sorry, it thinks it's just the regular single thread downloader, but it's actually going through only a section of the workload, and I just thread that out. And as it turns out, they didn't actually put a limit. This particular service, I reckon they thought that only the only people would use it through their front end, because they didn't actually put any rate limiting on it. So I found out I could just spawn as many threads as I wanted, send as many requests as I wanted, and it sped it up so much. And you could use async IO for this if you wanted to, probably, but I had already written the single threaded downloader. So in this situation, I think it was the right call to make. You know, I'm in a business scenario, time is money, right? I'd already written the single threaded downloader. It's trivial for me to just thread it out, get it done, get the information we need, and call it a day, rather than try and change the entire paradigm to async IO so that I can reduce the number of threads I have running at one particular time. But essentially, yeah, that was the deal. So I'll show you the worker thread here. So this was the worker thread. And essentially all it did, you know, was, and there's, as you can see, there's a whole bunch of code here. I'm not really going to show you guys, but yeah, it, you know, requested the data point, passed the response, put that into the data, updated the job statistics, and then this main thread just polled the job statistics that all the threads put in. Now, could I have done this better? The answer is yes. Python has events as a synchronization primitive. So essentially, you can have threads that block on events. And what I could have done here, instead of simply polling a number, which is probably not the best way to do it, you could say that's a race condition, but the fact that I was polling it every 200 milliseconds, it's probably fine. Like, it's updating fast enough that if I miss it when a thread updates it, who cares, right? It'll poll it and quickly grab it. But I probably could have used events for this if I wanted to be better. So you can see here, I'm just using a Boolean for the thread completion status. I could have just set an event because Python has that built in. So that's something to consider as well. Like, when you're threading, you can get away with a lot, but there's a lot of the times better ways to do it. And that's why I think it's good to go back and look at this old code I've written and see, okay, yeah, if I was writing this again today, this is probably how I'd change it. But yeah, so essentially the problem was all this data was not, it wasn't sequenced. Like, it didn't depend on the previous value. I had like thousands and thousands of data points, and the response from those that I got from the web API doesn't depend on any of the other ones. So the solution is, thread it out, send a whole bunch of responses, and I think I spun up about 20 or so threads. Like, I didn't want to send hundreds and hundreds of requests because that would just be rude. I mean, even 20 is pretty cheeky, but yeah, it sped it up quite a bit. This is the final example I'm going to go over with you guys today before we talk a little bit more about threading and synchronization primitives as general concepts. So this was actually a network socket server that I wrote up in a previous video I did on this channel. It's about an hour and 13 minutes. Check it out if you're interested. But essentially, this is another edition of the main thread worker thread paradigm. In this situation, what we do instead, we have this main thread, and its purpose, since this is a socket server, the main thread's point is to accept and delegate connections. So this uses what's called a thread pool based paradigm. So essentially, at the start of my program, I think I've defined up here or something, I have max workers. And essentially what this goes ahead and does is, at the very start of the program, just ignore my LSP errors. I don't have the dependencies in the right place for this example. But at the start of my program, I go through all the max workers and I just grab a whole bunch of threads. Like, I've got all these threads right here and these worker threads, and I spawn them in. So essentially those threads are mine. I don't have to worry about allocating them as the program goes on. I just grab them all at the start, and it's technically more efficient to do that. And yeah, I can just allocate them and use them as it goes. Like, I can do my own load balancing between them all and things like this. And we did a very primitive load balancer for this. It essentially just like filled them all up one by one. So it wasn't great, but yeah. Let's have a look at the worker thread. So the worker thread was essentially like this. So I had, I think, 8 of these is what I ended up going with. And this is epoll based. So what the main thread does is this worker thread just blocks on epoll events. And then it literally just goes and handles those epoll events. It does some protocol level stuff, makes sure the thing is valid, decides who to send it to, decides what to do with it, and then it goes ahead and does all that kind of stuff. You can see there I'm using a couple of a mutex locks there because there was some data that multiple threads might want to access. But essentially what this main thread here does is, we'll go down to here. You can see right here, when I get a connection, I find out who to send that to. I just do some sort of scan here and see, if they've got enough clients free. And then what I'd go ahead and do is add that file descriptor to the epoll event of this thing. So the worker gets another client that it's allocated to handle. So that's essentially what this goes ahead and does. So I've got this worker thread here, and it just waits on epoll events, and my main thread adds things to its epoll instance as the program gets under higher and higher load. So that's sort of the main thread worker thread paradigm. I've shown you those 2 examples here. So this one I showed you just before is where I've got a whole bunch of computation work or web request work that I need to get done that takes a lot of time to complete, and that's why I would thread it out like that. With this one here, it's more about load balancing. So I've got a whole bunch of threads I can use, and they need to handle multiple clients at once. So what I can go ahead and do is just have, these worker threads here wait on epoll, and then my main thread can delegate clients to those as needed. So, You can remove clients from them, you can add clients to them, things like that. So that's essentially the paradigm that I wanted to show you guys. I just wanted to take some time to go over the other synchronization primitives available to you. I've already shown you mutexes and some cases where Python-based events might be useful, but there are other ones available to you as well. So the first one we're going to talk about are semaphores. Now, semaphores are essentially, behind the scenes, an integer count, and what that integer count represents is how many threads can access one shared resource at the same time. Now, you don't actually have to implement them like that. They can be used for a whole bunch of other things as well. So you can use semaphores as a signaling mechanism, for instance. So a semaphore, you'll have an integer count, and when one thread essentially waits on that, it can decrement the count, and when another thread posts to that or signals to that, it can increase the count. And so essentially what you've got there is you've got a situation where you can either let a certain number of processes proceed with what they were doing, so you can use it for resource limiting if you like, or you can have it as a more like a lighter way to do signaling rather than, if you had a full-blown mutex. You can have a binary semaphore as well, which is essentially just a semaphore with a count of 1 that you can use sort of like a mutex, but it's generally recommended that you don't do that because there's generally no concept of ownership in semaphores. So with a mutex lock, you've got a concept of ownership where the thread that locks it has to be the one that unlocks it, whereas with semaphores, threads can do all kinds of stuff with them. But yeah, they're pretty interesting as well. Another thing I wanted to talk about are these read-write locks here. So essentially, a full-blown mutex just completely locks a resource, and threads that want to access it, usually they would block waiting for that resource to complete. But as this documentation from IBM says, you can have a lot of situations where you read data more often than it's written. So if you're full-blown locking a mutex just for a read operation, that might not be actually the most efficient way to do it because you're stopping other processes or threads from reading that as well, even if you don't have any intention to modify it. So you can use a read-write lock instead to lock it for reading, essentially, and then threads, any number of threads can come in and read that, and then when you want to write to it, you do that separately. So that's another thing. And briefly, Python has quite a couple of synchronization primitives. So you can see, if I just make this a bit bigger, you can see they've got lock objects, whereas are essentially like their mutexes, right? So you can lock stuff and unlock it, and you can block on that, you can poll it, you can do whatever. They have semaphores as well. The event objects that I was talking about before, so this is just, like a set or cleared, and you can block on that. They've got timers, barriers, all sorts of things, and then they've got some examples. So that's quite a bit of stuff available to you as the multi-threaded programmer, and it's up to you really to decide what fits best for your particular architecture. In this program that I wrote over here before, it would have actually been a lot better, and some commenters pointed this out, if I did decide to use a read-write lock for some of these mutexes. But it is, at the end of the day, what it is. They will work the same, but they might not be as efficient. So yeah, I hope this video was interesting to you guys, sort of goes over a bit of the way that you could use threading, whether you'd want to use threading, whether it's a good idea, and sort of how you'd go about doing that, and the sort of stuff that's available to you as a multi-threaded programmer. Cheers.